Welcome back, everybody. Just a quick set a few messages before we begin. So I will be in Norway next week, so then we can meet in person, all of us. And if you are interested, we could, if it fits, we could have an extended session. We could begin a little bit earlier, if you wish to. And then we could discuss more in detail about the second project. And that would be next Tuesday. So just send me a mail if you're interested in meeting a little bit before, because then we could have a slightly more extended session. But we will be in person next week. So the topic this week is to continue our discussion about the basics and mathematics of convolutional neural networks, so that you see how you eventually can build a code for neural networks. However, this becomes quickly involved, and we normally don't recommend building your own code. If you're familiar with Facebook's variant or library PyTorch, this is a very useful library which can be used for setting up convolutional neural networks. And similarly, TensorFlow with the API Keras are libraries which are extremely useful to use. And we will see examples of that a little bit later. So the basic mathematics which we discussed last week, let us try to repeat some of these elements. And then we are going to go back to the whiteboard and look at the type of hyperparameters which we have in the setup of convolutional neural network and the basic structures of convolutional neural networks. So there are several resources here, as you can see. You can look up these videos. There are also lecture notes, which are pretty good. There are lecture notes from the course IN 5400 at the University of Oslo, which is specialized on imaging. So the mathematics of convolutional neural networks is obviously based on the mathematical operation of convolution. And we have discretized and continuous versions. And mathematically, it's actually defined in terms of the equation which you see here. So you would have a function, a continuous function y of t, which is given by the product and with an integral over the variable a here, where you can think of this w as a weight function or kernel function, or as we will also call them, filter function, where you can actually filter away or modulate some of the observations which you've made. You could think of this x as being observations which you're making at given times, just as an example. And then you would filter away noise if you have the possibility to do that. And this w then represents a specific operation which is done on the data set which you have. But mathematically, it's expressed in terms of the integral which you see here. It's often written in a more compact form, like this x asterisk w as a function of t. And there is a discretized version, which you can rewrite in terms of the sum from a goes to from minus infinity to plus infinity. This can obviously be rewritten in a more efficient way when you're running calculations, because the values of a may be constrained to take values different from zero only in a specific domain. And that makes the multiplication here and the summation of the discrete events much more efficient here. So one of the examples which we looked at last time was the example of polynomial multiplication, which we can actually rewrite in terms of a matrix times a vector product. And this matrix had a specific name, as we mentioned last time. It's called a Toeplitz matrix. So let's look at that before we then move over to specific examples on how we implement the filtering and the type of hyperparameters which you will encounter when you're setting up a convolutional neural network. So I just wanted to go through these examples here so you see how these processes like a polynomial multiplication can actually be rewritten in terms of the mathematical operation of convolution. So the example which we looked at last time was that of a second-order polynomial being multiplied with a third-order polynomial. So that gives us a polynomial of degree 5. Normally, you never write out a polynomial times a polynomial when you write a code, because that's highly inefficient. And you can quickly multiply by or figure out the number of floating point operations yourself, and compare that with the efficient polynomial multiplication which we're setting up here. So the basic mathematics here is simply to realize that the multiplication of these different elements in a second order and a third order polynomial here can be rewritten in terms of these parameters delta, or these coefficients delta. And they are combinations of the parameters or the coefficients from the second order and the third order polynomials. And they are given by these equations here. And you note now that these alpha i's, they have values only between 0, 1, and 2. And same with beta of i's, they have only 4 possible values, which is obvious because they are second and third order polynomials respectively. So you can then rewrite these coefficients using a discrete convolution, which is now a sum from, in principle, from I equal to minus infinity to plus infinity. And you would typically rewrite it like this, or you can rewrite it as a double sum. Clearly here, you would never sum from minus infinity to plus infinity. You would only sum over those values of I where alpha and I and beta of I are different from 0. So that clearly simplifies things. And the more efficient way to code it is actually to rewrite it in terms of a matrix times a vector. So the process of convolution is a commutative process, which means that you can write it as alpha, the matrix representing the alphas, times a vector with the betas, or alternatively as a matrix involving the betas and a vector which involves the alpha. Actually, the second version here is normally the one you would use when you're setting up the process of convolution in convolutional neural networks. Something similar to this. And this matrix, which you see here, is called a Toeplitz matrix. So what it has, it has matrix elements. If you now look at this sub-diagonal here, it doesn't need to be a non-square matrix. It can be a square matrix. And you will have matrix elements with constant values along the specific diagonals here, or sub-diagonals. And typically what you will see is that they would be defined in terms of what is normally called a Toeplitz matrix. So that's a matrix in which descending diagonal from left to right has constant elements. If we rewrite the last matrix, we could just rewrite it more generically like this one. So Toeplitz matrices are very interesting. And in particular, for those of you who may be involved in Fourier series, you can actually rewrite, and you can see that, we can rewrite a Fourier series because the multiplication operator by a trigonometric polynomial compressed to a finite dimensional space can be represented by such a matrix when you're studying Fourier series. So Toeplitz matrices are matrices which appear quite often in discussions of convolution. And you see here the examples which we looked at is an example where we could either code it like this, and this is a matrix vector multiplication, which is going to involve less floating point operations. And similarly, this other matrix, which will actually involve a little bit more floating point operations. Now, one thing you will see now when we are going to studies of convolutional neural networks is that we can rewrite the process of convolution as a matrix vector multiplication, and this is actually the way a convolutional neural network is set up, but it doesn't always lead to a Toeplitz matrix. So sometimes, depending on hyperparameters called stride, we end up with a matrix which is called a circulant matrix. And we will see examples of this pretty soon here. So what you have here is some slides which we went through last time. And we discussed how to find the coefficients of Fourier series. And we also linked that with the convolution here, where we looked at the inverse Fourier transforms. And that could actually be rewritten in terms of, so if we have two functions which have been Fourier transformed, f hat and g hat, the inverse of that one can actually be rewritten as a convolution of the original functions f and g before you perform the Fourier transform. And I guess this is something you may have seen in mathematics courses when you, in previous years of study in your bachelor degrees, for instance. So what I wanted to say something about now, before we go back to neural networks, and in particular the convolutional neural networks, is a little bit about the structure of a convolutional neural network. And just to remind you, so you can rewrite everything in terms of a filter or kernel, K, and the equations which we had for this polynomial multiplication is an equation which was more efficiently implemented with this operation here, since it's a commutative process where I is the input and K is now a filter or weight function or a kernel as it's called. So it has different names in the literature. I tend often to use filter because you're filtering away some specific properties of the object. And just to remind you of convolutional neural networks, they have had their hugest success in imaging, and there are data sets with millions and millions of images which have been used to train so that you can recognize, let's say, specific types of animals or specific objects like houses, cars, or whatever. And the images are often really tailor-made. That means that this filter which you see here, or kernel, is often tailored to the specific situation which you have. So as we mentioned last week, if you have a house, there is no point in keeping the pixel information about the color of the house, because that is the same everywhere. But you would rather keep information about the corners, about windows, doors, the roof, etc. So that would be more important information in order to reconstruct the house. And then you just keep a few pixels which represent the colors. So deep learning libraries normally implement something which is called the cross correlation here. It looks almost like the standard convolution here. So the whole point is that you want to compress a little bit, the dimensionalities which you have. So you could now think of this as a dimensionality reduction method. And the example which we discussed last time was if you have an input vector of a standard neural network on a sound sequence data, you could have an input vector of a length 1 million, and you construct then a neural network with one hidden layer with 10,000 nodes. That means you would have something like 10 to the 10th weights to be determined, together with 10 to the 4th biases. So that means that the number of parameters is on the order of 10 to the 10th, even with such a shallow neural network. So the one of the things which we also discussed last time was the way you would implement this. And there's a lot of mathematics literature actually on convolution, where people try to make this more efficient. But the basic mathematics is something you can now see in this input matrix, which we have here. And then we have a filter, which is a 2x2 filter. And we have something which is called stride, which we are going to come back to and define again. We defined it last time, but I wanted to mention it again here. So what it means is that in this specific case, we are now going to, when we perform the convolutional process, we are going to take first this elements here and this one. And sorry, it's just the upper 2x2 block, which is going to be convoluted with a filter. And then we just move one step. So that means that we go from I00, and then we have the next 2x2 block, which is going to be I01, I02, and I11 and I12 here. Now to see what this stride actually means, let me shift to another set of slides, which is actually a little bit nicer than the ones which I have here. So this is taken from a course which is being taught at the University of Oslo, this IN 5400. So let me quickly just show you what this stride actually means. So we're just going to, I'm coming back to this one. So there are some nice figures here. So stride becomes a way by which you can filter out the different operations. So if you now look at stride 1 here, and you have an input which is a 7 times 7 times 1, so you have one color channel only, and you have a filter which has a size 3 times 3 times 1, so that means it is only one color channel. The stride is actually the way you can now tailor how this operation is going to take place. And you will see many different ways of performing this stride operation. But stride 1 means that the first block we are dealing with, since it's a 3x3 filter, we will deal with a 3x3 submatrix here. And then we move just one column at a time. So the next operation will be this block, which we're going to operate on. And then we operate with this block, and finally this block. And then the next step is actually to move down. So we would then move down to this block here, and then perform this square matrix multiplied with the weights. And then we will proceed till we have performed all the possible operations. So stride equal 2 means that we just move 2 columns at a time. And that means also that we will move 2 rows at a time. When we are done with the operations which you see here, when we have reached the other corner, and then we would then, instead of now moving 1 down here, we would actually move 2 down. So that will reduce the dimensionality of the output. So the filtering is a way to perform this dimensionality reduction. So I'm coming back to this on the whiteboard. Let me just go back to the Jupyter notebook in the meantime. And if you look at the operation which we have here, what we are going to obtain now is a new matrix. And I'm going to use a stride which is equal to 1. And we are coming back to that a little bit later on the whiteboard. But it means that I'm the first matrix element for the new filtered matrix, which is going to be a 2x2 matrix, is then given by I00 multiplied with W00, I01 multiplied with W01, etc. And you're going to get a matrix which is going to look like this. So this is my filtered output by the process of convolution. And you can rewrite the process you see here in terms of a matrix vector multiplication. And this is the way it's actually implemented in actual calculations in convolution neural networks. So the filtering itself, it mimics very much what we saw for this convolutional neural network, for this convolution process on the polynomial multiplication. So if you now look at your input, instead of writing this out as a 3x3 matrix, you would flatten it out and write it as a vector of length 9. And it would contain these matrix elements here. And then you would rewrite a new matrix, the filter matrix, which is a sparse matrix. And it means that what we can do now, so this is actually an example of a so-called circulant matrix. So there are lots of zeros, so you can actually utilize all the zeros and perform sparse matrix vector multiplications, which can be implemented very efficiently. And you can perform this matrix vector multiplication. So if I take this vector, which we have here, and multiply that with a matrix, that is the same as performing the convolution here, except that now this produces a vector. So this is a matrix of dimensionality 4 times 9. This is a vector of dimensionality 9 times 1. And that means that I produce a vector of length 4 times 1. I have 4 elements here. And if I want back a matrix, I would have to reshape the vector as a matrix, which is a 2 by 2 matrix. Alternatively, I can just keep the flattened out version. So what I get now is a vector of length 4 instead of the originally resulting 2 by 2 output matrix. So let's now go back a little bit and look at the kind of operations which we end up doing in a convolutional neural network. So there are several elements which imply a considerable degree of hand tailoring. So when you're using convolutional networks, and I know that some of you may end up using them in their thesis work, for the convolutional neural networks, what we end up with then is often to have some pre-trained network, which is used as an input to the data set which we are interested in. So just to give you an example, if you want to recognize bikes, you could have a huge library of pre-trained convolutional neural networks, which has been pre-trained on images of bikes. Okay, so let's take a look at the structure of a neural network, and let us try to set up the basic elements which we are going to need in order to eventually, if you want to write your own code, we can do that as well. But I would normally recommend using the functionality which you have in TensorFlow. So what I'm going to do now is more to present the different types of hyperparameters which enter and how you could set up the basics of a convolutional neural network. In the slides, you will find more information, but I just wanted to slow down the pace a little bit and jump into the whiteboard here. So let's do that. So here we go. So let me know if you don't see the screen here, but let's look at the basic structure of a convolutional neural network and the basic layout of a CNN. So we would have an input layer as before, and this is the vector or matrix which we defined as an I, and that contains a set of inputs. So this is our input layer. And we label this as an X. And this is now fed into a block here, which I'm going to call the convolution part, because the convolution part itself contains not only the mathematics of convolution, but it contains some additional elements. So we have something which I'm going to call the convolution part here. Just convolution or convolution part. And this contains now a block here where we perform this filtering, which I'm going to label with this W. And this is the part which represents the mathematics of convolution. And you will have parameters for the filters. So the filters connect to the input layer. And this is where we now perform the convolution. So we produce an output S, which is now given by the convolution of the filter with the input. And this can be done efficiently as a matrix vector multiplication, as we discussed. This is now fed in, this S here, moves then into a so-called ReLU layer, the rectified linear unit. And that produces a new output. So this is an activation function, which now takes the input from the filtered operation, where we have performed the convolution. And this produces now an output, which I'm just going to call S prime. And the filtering layer, this ReLU layer, has no parameters. There are no hyperparameters included here. And the only thing which is given here is the architecture of the network, which is reflected in the type of activation function. So the activation function has parameters itself. If you're using an exponential linear unit or a modified ReLU function, there will be some additional hyperparameters. But if you just take the standard ReLU function, which gives us output the maximum between 0 and the input which you have, then there are no hyperparameters here. So in the filtering process, you have parameters to tune due to the weight or this filtering matrix which you apply. And this is normally trained by the backpropagation algorithm. And then we have a new layer here, which is a further dimensionality reduction layer. And this is normally called a pooling layer. And I'm coming back to what this pooling is actually doing. But you can think of this as a further dimensionality reductions. So dimensionality reduction. And I'm going to show you examples of what type of pooling is normally used. The most common one is something which is called max pooling. So if you have neighboring results from the ReLU layer, which are then compared, and then you take the maximum value. So if you have 3 neighboring points which have this either the same value, you just keep one of them, or you just produce the maximum value from these 3 neighboring points, and you keep only that. So it's a way to reduce the dimensionality further. Now we're coming back to it. Now this produces now an input to an eventually a fully connected neural network. So this is often called the fully connected layer. So we just write it as a fully connected. And this is it can be a standard neural network where we now perform the standard matrix vector multiplications, standard NN. That's just one example. And this produces a final output. So let's just mark that one, and we're going to put it over here. So we have an output from the network. This output is then fed into a cost or loss function. And this is compared with the target values. So this is the basic structure of a convolutional neural network. And typically what you would have then is something which can be extended upon. So you're not limited to have only one convolutional path. You can have many stages of convolution. And what is often done in this kind of convolutional process, and by experience, if you reduce the image too much in just one convolutional stage, you will often risk that you lose too much information. So a kind of basic approach is to have a net which becomes deeper and deeper with many convolutional paths. So that means that you could even now filter it and produce new images. Instead of just one, you could produce 10 more, but they have been reduced in dimensionality. And then you can gradually filter the dimensionality out so that at the end, when you're plugging this into a fully connected neural network, you have already performed a reduction of the dimensionality of the image. So the basic layout now, when you're looking at the setup of a convolutional neural network, so the convolution stage itself has 2 new types of hyperparameters. So let's just now set this up, 2 new hyperparameters, which we also partly discussed last week. So one is called S, and it's called a stride. And the other one is called P, which is padding. So these are the 2 most important type of hyperparameters which we end up with. And then you have further hyperparameters which you can have eventually in the ReLU layer. but right as of now, we're just going to keep this ReLU layer as something which is defined by this ReLU function, which just takes the maximum value of the input. And you will also have an additional hyperparameter, f, which is the dimensionality of the filter. So let's now look at the example which we had in those slides. So let's suppose we take a 7 times 7, and it's actually times 1, so it's only one color. You have typically 3 color channels. So we have an input image. So this input image has then an n. I'm assuming that they have a square image. And then we have a filter, which is a 3 times 3 filter. It's actually times 1. So this is our filter. So we would then have an f, which is equal to 3. And then I'm setting up a stride, s, which is equal to 1. So these are going to be the parameters which I'm setting up in this operation, which I'm going to show you an example of now. And then I'm going to define something which is called padding, which we briefly mentioned last time, but I'm going to mention it again. So p equal to 0. So if we now look at the operations which we are going to do now, if we now set up this 7 by 7 matrix. So we have 1, 2, 3, 4, 5, and 6. So that should be 7 slots. So when we now have a 3 by 3 filter, which is convoluted with this image, what we will do now is that the process of convolution means that we are going to act on a 3 by 3 block. This is the first block we're going to deal with. And that's being filtered with the kernel or the filter matrix. And then the next block, since we have a stride equal to 1 here, it means that we just move one step along the that specific set of columns which we have picked up. So it means that the next block is going to be this one. And then the next one is going to be this block here. And then we continue like this till we have emptied. So we started there, and then the next block would be this one. Oops. So that one. And finally, the last block is going to be the block which you see here, which is going to be this last block here. Then we continue along these lines, and then we would move here, and we would have a new block here. And this just gets repeated till we have now gone through the whole matrix. So we are going to get blocks which look like this. So the output is now going to be a matrix which has dimensionality 5 times 5. So let's see that. So we will have a matrix. S is the output matrix. And this is going to be a 5 by 5 matrix, and you will easily see that because the type of blocks which we're going to set up now. So this is the matrix S. So the first block is the one which we marked in red. So that means that we are going to have the first block is going to be this one. That's the effect of the convolution. And you saw that we had 5 different blocks when we had stride equal to 1, with stride equal to 1. So the next block is the orange block which we put up. So this is the effect of the convolution with the filter and the input matrix. And then the next block, if I now can see my colors correctly, should be the brown block, like this. And then we had a dark blue block, which is this one. And finally, we had a totally dark block, which is this one. And then we continued with the pink block here, which is this one. And this just continues all the way till we are filled in all the different slots here by the convolutional process. So every time we perform these operations, there is a set of convolution processes which take place. So it means that there are three matrix elements, three by three matrix here, which is convoluted with a 3 by 3 filter. And the matrix element which we end up with in here and so on is the result of the convolution for every stage here. So this is with stride equal to 1. So if I have a stride equal to 2, then I'm going to get a slightly different matrix. So if I put stride S equal to 2, then we are actually going to obtain a matrix S leads to S matrix S to have a dimensionality which is given by a 3 by 3 matrix. So you can easily see this by the following formula when we are looking at the output size. So what we have is that the output size can be easily calculated by the following formula. So we have the dimensionality, and now I'm looking at the square matrix. And I'm going to change this formula when we are looking at a matrix which is non-square just a little bit later. So we would have n minus f. F is the dimensionality of the filter. So still a square filter divided by stride plus 1. And you can see the example here if we put n equal to 7. So this is now the output, n equals 7 and f equal to 3 and stride equal to 1. Then it's easy to see that 7 minus 3 is 4 divided by 1. 4 plus 1 has dimensionality, which is equal to a 5 by 5 matrix. Then if I take the stride equal to 2, I just change it, n equals 7, f equal to 3, same case, and the stride equal to 2, that gives me a dimensionality, which is a 3 by 3 matrix. So the typical dimensionalities of the filters, which you will encounter in many of the applications and implementations of convolutional neural networks, are filters of this type here. That's a typical size. And it's common to have a stride equal 1 or stride equal to 2. In the lecture notes, there is a link to a scientific article, which is just called the arithmetic of convolutional neural networks. And they discuss all the different types of filters which you can have. So this stride is not something you can only decide to apply on the blocks as we did here. So what we did here was a repeated operation on sub-blocks of the matrix, of the original matrix. But you could actually, instead of taking the sub-blocks of the matrix, you could just take, say, this matrix element, this one, and that one. And then you would continue like this. And this depends very much on the type of image which you have. So the filtering can actually be tailored to the actual image. And as I said, if you take an image which has a, let's say, 200 times 200 pixels, no colors, many of these images, they may contain information which is not that relevant to keep, like the painting or the color of a house. And that means that there could be elements in these pixels here which are just less relevant. And then you would really tailor this kind of filtering to that specific input data. So just keep in mind, you're not limited to proceed like block by block here, like I did now, but you could take this one, that one, that one, and that one, and then continue like this till you've gone through the matrix. And there are tons of these types of filters which are being applied. This is actually something which has also led to ideas about dimensionality reductions in solutions of differential equations. So in the last years, there's also been activities in finding filters which can reduce the dimensionality of a, let's say, a differential equation, and you would proceed then by using convolutional neural networks. Okay, so the type of output which we get depends on the type of filter. So another thing which we didn't talk very much about is this issue of padding. And we mentioned it last time that the padding is something which serves to avoid that the corners are less represented in a filtered image. So if we now go back to this other parameter, which is called padding, in the case which we had here, we had padding p equal to 0, but we can actually add padding to the image. So that means that if we have an image which is now represented by this input matrix, since the corner values which you have here and here, so everything on the border is normally represented when we did this stride 1 operation, these corners are typically just represented in one of the filtered parts of the new matrix. And what is common to do then is actually to add an outer layer here. So you can have a larger padding if you want to, but it's common to just have a padding equal to 1. So that means that you plug in zeros here. And then you perform the convolution of this extended matrix. And by doing that, you will obviously have several zeros which appear. But what happens then is that the layers which you have, which are represented by the outer layers, they will now be represented in more than just one slot in the filtered matrix. So padding is something which is often used, and it becomes a new hyperparameter. So this padding is a new hyperparameter. And you will see that in the setup of a neural network, you will actually have the possibility to define the stride and the hyperparameters. Was a question?
Yes. Padding p equals to 0 means that you have margin or not?
Yeah, exactly. So you just put the values to 0, but when you perform the multiplication, then what happens when you do the filtering with convolution, then it means that this matrix element, which you have here, for instance, this one, will appear in more than just one of the positions in the convoluted neural network. No, sorry, in the filtered matrix.
Yes, but I mean, it's for notation. When you say that p equals to 0, is that you have a padding of zeros, or that you have no padding?
So padding p equals 0 means no padding.
Okay.
So let me just be precise here. This is no padding. And the case which you see here, we have one outer layer here. This is p equal to 1. So here I have padding equal to 1. And then you can actually change the formula which you had for the setup of the neural network and for the set of the output. And you would simply add padding to the expressions which you have here. And we will see that after the break. So I suggest we take a small break now, if that's okay with everybody. So what I wanted to do now is more to give you the kind of basics of a convolutional neural network. And before the break, we discussed these hyperparameters, padding and stride, and how we can actually perform this type of convolutional operations. So if we look at the typical convolutional part, what you would have then is the following. If we summarize, so typical convolution part. What we have then is one or several convolutions. So with convolutions, it means actually the filtering in parallel in order to produce reduced images in parallel in order to produce use a set of and these results are what we call linear results. And linear because we actually are performing a standard convolutional process of linear results, which are then fed into these activation parts or this ReLU part. So a set of linear results, which are then fed in to a so-called activation part, to an activation part. Now, this activation part is often given by a linear function like the ReLU function. So each linear activation, so the most typical one, which is actually used in these convolutional neural networks, is the ReLU function, the rectified linear unit, which simply takes the input and finds the maximum value between 0 and the input you're feeding in, and that is the output of the ReLU layer. So that means that there are no hyperparameters here. Each linear activation inputs these inputs to the linear activations are run through in principle a nonlinear activation function. You're not limited to the ReLU function. You could have used a exponential linear unit. You could use a tanh, you could use a sigmoid function. But what comes into play here is actually the number of floating points you are willing to spend and the derivatives of these functions, which become important when you're now trying to find the optimal weights and biases later. So you would now have inputs are run through a nonlinear activation function. So that defines also the architecture of the neural network. And then there is a final stage, which is called the pooling stage. So you can read the pooling stage as a further dimensionality reduction. And this deals with something which is normally called sparse connectivity. That's another name for it. So the pooling stage means that if you now look at the input to the pooling layer, suppose you have 4 specific nodes here. So this is something which would come out from the ReLU layer. So with sparse connectivity, it means that not all the nodes are connected. And then we are looking at the nodes in the pooling layer. So this would be the pooling. So the sparse connectivity, which you see here, is different from the ones that you have seen in a standard feed-forward neural network. So if we're now putting labels on the different nodes here, so we have a node 1, 2, 3, and 4. In principle, you have many more, actually. So with sparse connectivity, what it means is that not all the nodes in the input layer, which in this case is the output from the ReLU function, are connected with the next layer. So in a standard feed-forward neural network, you would have a dense connectivity, which means that all the nodes in the previous layer are connected with all the nodes in the next layer. So this means that in our case, when you look at the outer nodes here, they connect only with 2. So this will be a connectivity of 3. So if I look at the next ones, So if this node here would be now connected with 3 nodes in the next layer, so the connectivity is equal to 3. I would have the same with the next nodes. So this will be connected to 2 here, to 3 here, and 4 here. And finally, the outer nodes connect only with 2 here, in this specific case, which we have set up here. So suppose now that we assign some values from the ReLU layer. So this node 1 produces a value of 0.1. Sorry, this produces a value of 1. This produces a value of 0.2, and this produces a value of 0.1. So one thing which is done in order to produce the next values, when you look at the nodes which are connected, is a standard technique which is called max pooling. So that means that if you now look at the nodes which are connected here, this node here feeds in a 0.1 here, but this one feeds in 1, and it feeds in 1 here, and it feeds in 1 here. So what we end up with then is to take the maximum value, 1 here, 1 here, and you see now that the node 2 here feeds in 1 here as well. This node receives 0.1, 0.2, so it takes the maximum value. So this also produces 1. And then the final node produces 0.2 here. So this is 0.2 because we are feeding in 0.2 and 0.1. So the values which you see here now are the maximum values. And what you can do next is also to downsample the number of nodes, because we have 3 nodes now which just output 1, and there is no point in keeping the information from these 3 nodes here. We can just keep 1. So max pooling is often followed by something which is called downsampling. So in the ReLU layer and in the pooling layer, there are no parameters which are adjusted. The parameters which appear in the convolutional part are essentially the parameters in the weight matrix. And the pooling layer, typically just if you use max pooling here, that simply produces as an output the maximum value for the nodes which are connected. What you could say now is that the connectivity between the different layers, so like in this case, we have a sparse connectivity, the connectivity becomes a kind of hyperparameter which you can tune and decide upon. So if we now look at a specific example of the number of parameters which we will need to train. So suppose now that we have an image with an input volume, and we have 3 color channels now. So we have a 32 times 32 times 3. So that's the input image. And what we are going to do now is to, instead of just producing 1 output, we are now going to produce 10 outputs from the convolution stage. From convolution. So the whole filtering process is going to be a series of such operations where you gradually reduce the dimensionality of the image. So you could have 10 outputs from the convolution, and you would have filters by 5 by 5. And then with stride equal to 1, for instance. Again, the stride parameter is something which people play around with. And no padding. So let's assume that. So if you look at that image here, then we would have 32 minus 5, which is a filter, and that's a typical dimensionality of the filter, divided by 1 for the padding, plus 1. So that means that we get 28. So the new image, since we also produce 10 images, then we have 28 times 28 times 10 images. And in addition, we have plus 3 color channels. If we look at the filter, the dimensionality which the filter has. So it has 5 times 5, and then we have the 3 color channels plus 1 for the bias of the filter. So this is a number of parameters which the filter has. So that these are the parameters which we need to find by the backpropagation algorithms. So these are 76 parameters. And then we have 10 images. That leads to 760 parameters to fit in the convolution stage. You can compare this one to a hidden layer in a fully connected neural network, where you feed in the image, which is a 32 times 32 times 3. So that means that you would have a dimensionality of the input layer, which is close to 3000. And if you then have a hidden layer with 100 nodes, that means you would have 3000 times 100 roughly. This is a rough number, weights to adjust. So in this case, with the filtering, you have only 670 parameters, whereas in the other case, if you just take a standard affine transformation given by a standard feed-forward neural network, you would have 32 times 32 times 3, which gives you close to 3000 input variables, times 100 hidden nodes. So that means that you have you would have something like close to 300,000 weights to fit. So this is a considerable dimensionality reduction. So the way you do the filtering is obviously something which depends on the type of image which you have. So if we now want to look at in summary here, what you could do is to run this filtering again and again. And this is pretty common. If you look at large data sets like ImageNet, they have several convolutional layers where you're actually filtering your image gradually. And then everything ends up in, let's say, a fully connected neural network. So in summary, if you now want to look at the dimensionality here, or the total dimensionality which you end up with, so what you would do now is to accept a volume of the following dimensionality of, so this is the original image. So you have the width 1, and then the image has a depth, which I just call D1, and then it has a number of sorry, not D there, it should be H. So this is the height times the depth. This is a number of parameters. So we would normally call this the width of the image. This would be the height. And this is the depth, which for an image is normally given in terms of the color channels. So that is the dimensionality which you feed in. And then what you need is 4 new hyperparameters when you're setting up the convolution stage. And these parameters are K, which is the number of filters. And then you have F, which is their spatial extent. So the filters are normally taken to be given by square matrices. So their spatial extent. And the typical spatial extent is to have a filter of dimensionality 5 times 5 or 3 times 3. These are the most common filters which are used in many of these convolutional neural networks. Then we have the stride. And this is something which is often hand-tailored to the specific images which we have in the specific problem. And then we have the padding. And this is the padding of zeros. So that produces an output. And this output is given by a new object, which has weight W2, has a height H2 times a depth D2 here. So the weight here is given by the weight of the first matrix, the input matrix minus F, plus 2 times the padding, divided by the stride, plus 1. And then I have H2 here, which is now given by H1 minus F, plus 2 times padding, and divided by S, plus 1. And this depth is now given by the number of images, which we are going to produce now. So the number of filters. So that what you get then, we get then F times D1 weights per filter and K, so this is the number of filters which we are setting up, and K biases, so this is the number of parameters which need to be tuned in a convolutional neural network for the convolution stage. And these are parameters then which are trained by backpropagation. And K, this number which you have, the number of filter, is often chosen in terms of, or chosen in powers, chosen in powers of 2. You will often see that in many of these applications, you would find that you use the powers of 2 as a way to set up matrices, etc., etc. So the common settings, which you will often encounter, is F equal to 3, S equal to 1, and padding equal to 1. You can have F equal to 5, and S equal to 2, and padding equal to 2 is another common setting. Alternatively, you have F equal to 5, S equal to 2, and then you can have paddings which are 0, 1, and 2. So these are pretty common parameters in setting up many of these neural networks. So this sets up the basics. And as I said, many of these neural networks are really fine-tuned and tailored to specific problems. So one of the things which I just wanted to continue with are these slides from the University of Oslo here, which give you a more kind of visual view on the setup of a neural network. So I just need to find back the slides. Why did I put them here? There we are. No, that didn't come here. So let me just try it again. So hopefully you can see these slides now. So these are taken from a course which runs at the University of Oslo, which is called IN 5400, which is actually specialized to the structure of neural networks and convolutional neural networks. So if you now look at a typical setup of a neural network, so let's just bring up this type of images. So this is the kind of example which I gave you. So you have an input layer, which now contains all the information about the image. And then you could convolve or this with a given filter. So you could have a 5 by 5 times 3. This is one typical filter which you can set up. And then you can now produce many of these filters. The input volume and the filter have always the same depth, which is the blue value here. So we want to keep the color channels. And typically now when you set up the convolutional layers, you have a filter here, which now reduces the dimensionality of the image. And you would then produce this by doing a convolution with a 5x5 filter. And that produces an image which is 28 times 28, one here. And then you would now keep adding the different colors, so you can actually produce many such copies of the image. So in the case which we looked at, we produced something like 10 images. So you can continue and produce many of these images. So this would be the first convolutional layer. And then you would use an activation function separately on all the elements of the output volume. So we perform the convolution here. And then you can set up a new convolutional layer. So you would have convolutional plus the ReLU. And you can do a new convolution in ReLU. So you can reduce the dimensionality. So you have a new filter, 5 times 5. And that gives you 24 times 24. You can produce 10 images. And you can continue like this. So as you see, the process gets very much hand-tailored to the type of images which you want to deal with. So this sets also the type of hyperparameters. I'm going to send you this file so you can take a look at it. It's actually pretty, it can be pretty useful because it gives you the kind of overarching features of a convolutional neural network. So what I wanted to conclude with now today is actually the way we can now set up a convolutional neural network and how we can, oops, not that one. So I have too many windows which are open here. Here we are. So this is my convolutional neural network. So in the slides, you will find more information about this different parameters, but I actually recommend to take a look at the paper by Dumoulin and Visin on arithmetic of deep learning, where they actually go through many of the basic steps of convolution here. So I'm going to skip this because these are things which we have been looking at in the slides. So what I wanted to finalize today with is how you can use Keras to set up a convolutional neural network. We are going to end a little bit earlier today, by the way, because I have a meeting which I have to attend. But if we now look at the setting up of a convolutional neural network, if you take this original MNIST data set, this is a data set which has 28 times 28 pixels. And that means that you would have 724 weights to each neuron in the first hidden layer if you just run this with a standard feed-forward neural network. If you were to analyze an image which is larger, you would have 128 times 128. So that means 16,000 weights to each neuron. And if you're dealing with color images, you would have to multiply this with 3. So the layers of a convolutional neural network then, as we have been discussing, you have the filters, you have the rectified linear unit, and then you would have a pooling layer. And that reduces all the size of the convolutional layer by taking the maximum or average across some small regions. And that serves as an input to eventually the next convolutional layer. So there is a systematic reduction of the size of an image through different convolutions and poolings. So you're not limited to only one convolutional layer. But if you want to write, let's say, your own code, I would normally recommend just using one convolutional layer at the beginning. So this is the MNIST dataset, which are these handwritten numbers from 0 to 9. And I'm going to show you how you can set up this one using a TensorFlow. So the images are pretty blurred. I would actually have problems in recognizing some of the numbers. I can see that this looks like number 7, but I would have problems with this number here, this number 8. The 3s and the 7s are a little bit easier. But this is a data set, and this data set is actually a data set which is trimmed down from the original one, which has, I think, something like 60,000, 70,000 images. and the size is 28 times 28, I think, and you have only one color channel. So in this case, it has been trimmed down to 1800 and 8 times 8 pixels. So the way you will set it up now is to use Keras, which is an API on top of TensorFlow, which makes it a little bit like a black box like environment, but it's easy to set up the basic elements, and then you can dive more into the details if you're interested. So you need to set up the inputs, data sets, layers, and models you want to include. It's a sequential neural network, so you just move forward and backward. It's going to be a dense. You need to include the optimizers. You need to include what kind of regularizers you want to have. And then you also need to define what kind of output you want. So this is a categorical output, which means that we are going to have 10 categories, which are the handwritten numbers from 0 to 9. So this is 10 categories here. And then I split my data in train and test. So these are just the standard things you would do. And then when you're running with Keras, what I'm setting up now, so let me just reduce a little bit the dimensionality here. So I'm setting up my neural network. So I just have written a function here, which I call convolutional neural network. And it feeds in, this is my function. It takes the input, the type of fields I want to have, number of filters, number of neurons. These are parameters which I want to define, the learning rate, and the hyperparameter lambda. So what I'm setting up now is a convolutional layer. I have the field I want to set up, the input shape. I want an activation, which is a relo, and I'm having a regularizer, which is a regularizer of the type of L2. I define the pooling, so I'm going to use max pooling here, and the pool size is 2 by 2. I flatten it out, so that means that I convert the output into a long vector, and then I have a dense layer, as you can see here. So that is just a fully standard neural network, and in this case, I also have an activation function as a relo function. The regularizer is a norm2 regularizer. And then finally, I have my output layer where I have the activation function, the softmax, and then I have the same regularization parameter. And then I define the stochastic gradient descent with a learning rate here as my optimizer. And then the loss function, which I want to compute, is the so-called cross entropy. And this is the simplest way by which I can set up the convolutional neural network with Keras, where I have one convolutional layer. There is a max pooling. I flatten out everything, and that's fed into a dense neural network. And then I have a final output layer, which is now given by this one, where I have a softmax activation function. And I have 10 classes I want, or categories I want to classify. And you can see here, I need to set up the number of epochs, the batch sizes, the number of filters I have, number of neurons. So this receptive field is the definition of my filter. So I have a 3x3 filter. I haven't defined the stride. So the stride, if I don't define it, by default is put to 1. And if I don't define the padding, I think the padding is by default set to 0. And I set up a number of hyper parameters lambda, and I have the learning rates, so which I just set up in terms of 2 brute force grids here. My final part, I just run over the hyperparameters and the learning rates. I do the fitting of my convolutional neural network, and then I evaluate the score, which is just the accuracy score. And with that one, I can run the network, and this is actually going to take some time here. So we don't need to wait for that. And you can finally visualize it by using Seaborn, and you can compare that with a standard feed-forward neural network. So what you're going to see is actually that this convolutional neural network is actually going to give us results which are not as good as those which we got with a standard feed-forward neural network. So it means that for this specific data set which we have, a standard feed-forward neural network is actually doing a perfect job. Now, I'm going to stop here today a little bit earlier, and because I have to be at a meeting pretty soon. So we are going to, next week, we are going to continue a little bit the discussions on convolutional neural networks and how to run them. And then we are going to move into recurrent neural networks, which are also relevant for the solution of these differential equations. And if we get time, we will say something about autoencoders and generalized adversarial neural networks. But I'm going to stop here today.